Okay, so today we will, the ultimate goal is to explain the AlphaFold. However, I thought without giving some kind of background, it might be misleading how we arrived at the protein structure solution. So I created a little history of protein, how the modeling of protein structure evolved over the year. And then hopefully, at the end of this guide, Hitchhiker's Guide, you'll have an understanding what AlphaFold is trying to do, how does it predict the structure. And then after my talk, Daniel is going to go over a little bit in the details of the machine learning part that is the engine of the AlphaFold. So what is the basic dogma of protein structure prediction? Okay. So Christian Anipson was working at NIH in 1970s and got the Nobel Prize, I believe, in 1972 in chemistry. And he first came up with the thermodynamical underlying theory for protein structure prediction. And then the underlying dogma is, if you have the similar chemical structure, that means similar amino acid sequence, between two proteins, their structure should be similar too. Okay, and then he showed through multiple experiments where it disrupted certain disulfide bond in the protein, but kept the same amino acid sequence, and those protein ended up having the same structure. So that was the underlying dogma. That means, like, if I have similar sequence, I should have similar structure. Now, I should warn you, though, this is not universally true. It is true for most of the cases. There are very specific cases like Alzheimer's disease, the protein that causes Alzheimer's disease, or prion diseases. Those proteins can have totally independent two different structure. Alpha helical structure and beta sheet structure. They're totally different. Okay, so this approximation is not universal. However, it obeys for most of the protein that we will come across. And that is the fundamental dogma behind the protein structure prediction. So why should we go for modeling? The reason being is the sequence technology has improved so much, and it's really cheap to do sequencing. So right now in GenBank database, we have 2.6 billion sequences, right? And those are nucleotide sequences. And all we need to do from nucleotide to translate it to a protein to run some computational algorithm, we still do not have resources to or time to run all of those, translate all of those. We're able to translate about 200 of the available sequences right now, and they are deposited in the UniProt. UniProt is a wonderful database. It's so rich. I do not know at the end of my talk if I'll have a time to just go over the UniProt. But whoever is interested, we can make a separate session, because if you're working with a protein, the UniProt has all the data combined together, structural, chemical, post-translational modification, mutation, everything is there. So if you're working with a new protein, or if you're working with a new project, UniProt is a good place to start. So there are 200 of deposited in the UniProt. And then you already came across PDB. Currently, there are roughly 180,000 structures in PDB. So you see the huge gap. We have 2.6 billion sequences, and we have only 180,000 structures. And then this gap is widening. It's not that we are catching up. Like right now, we are only have structure than less than 0.1%. That number was 2% in 2004, 0.7% in 2010. So experiment is never going to catch up. So that's why we need to do the modeling. At least we have an idea what information can I get out of the sequence. There are typically three kinds of experimental techniques. And I'm going to go into a little bit detail because when I was preparing this talk, I realized how much some of the philosophy behind the experimental techniques got translated into the protein modeling. So the first one is X-ray crystallography. In X-ray crystallography, you have to crystallize the protein so that all the protein molecules are in a array, like they're in a very organized array. And then you send the X-ray beam. And once you send the X-ray beam, you'll get a diffraction pattern. So what you're looking in that diffraction pattern, that's in your Fourier transform space. That means like if you take the Fourier transform of the diffraction pattern, you'll see certain bright spot. And then you can translate into a real space. And that's the next step where when you translated that Fourier transform space to real space, you get a density. And that density reflects how the X-ray beam got reflected or deflected by the structure of the protein. So the next step is from that density, how do we fit which atom is where? Okay. And you have an idea about the sequence of your protein. Then initially you start doing manually, but as the protein gets bigger, then de novo design fitting on the electron density map is not always possible. So one of the things that in the X-ray crystallography, the experimentalists do is called molecular replacement. That means like, if you know certain side chains or certain part of your proteins exist in another crystal structure, you take the density from there and you say like, oh, this is where this part will fit in my current. So molecular replacement theory has an equivalence in our protein structure modeling. We'll come back to that later. The second part, which is currently really hot, is the cryo-electron microscope. In the cryo-electron microscopy, instead of a crystal, you freeze the protein in a thin ice. Okay. So in X-ray crystallography, all your proteins are arranged in the same way because otherwise you don't form a crystal. In cryo-electron microscopy, everything is arranged randomly. So you do not know about your orientation. And it's in a thin ice, and then you send the electron beam. Okay? And you collect the information actually in real space. You do not have to go to a Fourier transform space, but you can. The trick behind here is like an electron beam is way tinier than an X-ray beam. So in theory, we should be able to see more in a cryo-electron microscopy than an X-ray. Problem being is electron is more damaging than X-ray, so you cannot send a lot of electron beams there. And that's why the signal to noise ratio is high. And the processing is there. How can you reduce the signal to noise ratio? And also remember, there's another part. We do not know the orientation of the protein. In X-ray, everything is in the same orientation. So that's the cryo-EM part. So these two, even in the cryo-EM, we use something like molecular replacement. In the sense like we see like, oh, something looks like alpha helical. We have seen this in a before. So we'll fit an alpha helix today there, okay? And then there is a third technique for which we have experts here, Travis, Michelle, is the NMR technique, okay? So in NMR techniques, what you do is like, you have to level your residue. That means you have to put certain kind of residue with a different atomic weights, like same atoms with different atomic weights. And then when you turn a magnetic field on, those atoms will be aligned with, because they have magnetic moment, they'll be aligned in certain direction. You turn the magnetic field off, then they'll be like slowly rotating and falling back. Now, depending on how two atoms are close to each other, this magnetic falling back will be perturbed. and you can create a distance restraints called NOE, nuclear overhauser effect. So you can create a NOE distance restraints from like how the, once you turn off the magnetic field, how the atoms are coming back to their original position. So when you run these kind of experiments, you come up with lots of distance restraints. And then you can run a simulation where you try to satisfy those distance restraints. And after, if you have enough distance restraints, if you run the simulation, you should come up with a typically multiple structure that, this is the NMR spectrum, which tells you like how once you turn off the electromagnetic field, how they are receding to their original position. And when you run from there, if you have the distance constant, if you run the simulation, all these structures satisfy the distance constraint. And we have an equivalence to that in our structure modeling too. That's why I'm going through a little details here. And we'll come back to that equivalence later. So these are the typical three structural techniques that we use here, okay? So, but as I said, like a structural techniques, experimental determination of structure takes time, costs a lot of money, it costs a lot of time and resources. It will never catch up with sequencing. Because nowadays you already run Illumina sequencing can do, 48, 96 samples in a matter of hours. And so there is no way you can, the structural material will catch up, experiment will catch up with that. So that's where the protein modeling comes in, okay? Now there is a long history of protein modeling. And typically, there are lots of different methods. You can put them in two different methods. One is the template-based modeling. The template-based modeling means like, something like molecular replacement that I told you. I have seen this before somewhere else. Can we take that from there to my unknown structure? Okay? They're very similar to the idea of molecular replacement in cryo-EM or X-ray crystallography. The other part is template-free modeling. That means like, I'm not going to rely on existing data. I'm going to start from the scratch, de novo. And the first instance of template-based modeling was in 1969. The structure of the egg white lysozyme was available. At that time, the algorithm for alignment which Travis went through was not discovered. Okay. So Brown et al., they manually aligned the alpha lactalbumin with each other. And then they use the idea like wherever they are similar to the lysozyme, the sequence is similar, the structure should be similar, okay? And there's no visualization available. So they created a wire structure. And when I went to Purdue, I saw some of those wire structures. They're still kept there. You can go around and see for a different protein though. And then wherever the protein amino acid did not match, then they try to fit it. Okay? There are Ramachandran plots and other plots which kind of tells you how the side chain should be arranged, gives you some indication. So that's how they try to fit it. Okay, that was the first instance. So even though it is very preliminary, there are 4 basic steps that you can identify from that first 1969 paper. They're still valid. Number one, for a template-based modeling, you need to have an experimentally solved proteins. That means you need to have a template, okay, your PDB. And you have to use some kind of alignment. And now the alignment algorithms have improved so much. You can do multiple sequence alignments. But this is very important. Your structure quality depends on how well you can align. And then this is called threading, the technical term, where you transfer the known part from your known solved protein to your unknown modeling. Okay, that means like you're threading it. And then finally, you, whatever you're not known, you try to build it. And we'll see how that is done in the modern software. Now, there are lots of softwares, algorithms that does template-based modeling. Until AlphaFold 2, iTester was a very popular one. And then the way the iTester does is like, they take your input sequence, they break it into overlapping, I think 9 residue, I believe it's 9 residues, some of the overlapping windows of 9 residues. So that means like 1 to 9 is one fragment. Let's say 7 to 16 is another fragment, 14 to 23, another fragment. So if they break down the sequence into multiple fragments, and then you look for structural similarity for those fragments. That means like templates, okay? Once you get the template, you start threading them in. And you put, whatever you can. So you will have a, some part of the protein where you can feed up the different fragments. And then you start like combining the fragments and see how the, your template, once you have completed the template, how they're distributed. If there is a big cluster with similar structure, then that's probably your answer. You take that center of that cluster. Now remember at this time, this is highly, it's not relaxed because you just combine different fragments together. So then you can reassemble them to relax them a little bit. That means energetically you relax them and you take the minimum structure, add hydrogen bond and so on. Okay, so the idea behind it here is instead of looking for your template for your full protein, which is very hard to get, very rarely you'll get the full template, you break down your protein into small fragments and you look for the template for the small fragments, and then you find a way to assemble the different fragments, like our molecular replacement. So there are lots of software that does these. I'm just going to the one, highlighting one, which is the iTester. And here are a list of software. I'll share these slides with in the Slack. Modeler, who use Shudip's software use Modeler for the loop modeling. We'll come across Rosetta. Rosetta has multiple functionalities. One of them is template-based modeling. They do it. Swiss model or Fire2, these are all very popular. Now, again, remember, any template-based search relies on how good your sequence alignment is. Travis went through it yesterday. If you do not have a good sequence alignment, you cannot find a template, your structure prediction will not be good. Okay. So I think like already Travis shared some of these MSA servers yesterday. So as a rule of thumb for protein, if you have greater than 50% sequence identity, you are going to get a really good structure. Okay. If it is between 30 to 50%, you'll probably get the core of the protein right. That means like your secondary structure core, alpha helical bundle or beta sheet bundle, you'll get that right. But the tertiary, like on the part that are not near the core, you probably won't get it right. Now, if it is less than 30, some people say 20, 25, whatever, it's called the twilight zone. At that time, you do not know if you are going to get a right answer or wrong answer. Okay. Theoretically, you should be able to get at least a decent model, even at the level of 25% sequence identity, or that practically it hasn't been achieved. Okay. So I think the take-home message is if you have between your query and one of the solved structure, more than 50% sequence identity, you can easily use template-based modeling to get a more accurate structure. Now, the template-free modeling, and I'm not going to go into details, the reason is you have been taught full day on molecular dynamics and molecular mechanics. The first thing that comes into template-free modeling is the molecular dynamics, in the sense that we'll calculate all the physical forces between the atoms, we let them evolve using Newtonian mechanics, and see where do they arrive. A brief history of molecular mechanics and in terms of protein structure, the formulation of thermodynamic hypothesis was in 1973. The first molecular dynamics applied to study protein. Well, actually, I missed a name. The first molecular dynamics proposed that molecular dynamics, something like that, can be used by Rahman. Indian scientist was working at the Argonne lab. He got recognized way later. Now there is a Rahman Prize from computational part. So he did on inert gases. But the first one who applied on the protein motion is Martin Karplus, 2010 Nobel Prize, 2012 Nobel Prize, I forgot the year. And he did not invent amber, he did not invent Gromax, he came up with charm, the best one in the field. So anyway, so that's the first one. He developed molecular dynamics that charm is a little clunky compared to amber and Gromax. However, it has a lot of interesting stuff in it. And then amber was developed pretty soon after. And I don't think this is right. I think this is the paper that first came out in 1983 between Barney Brooks and Martin Karplus. The template-free modeling means like, I'm going to calculate physics force between all the atoms, and I'm going to see if I can predict the protein structure. Let's see. And then if we go down that road, the few things that I want to point out is the CASP. In 1994, this CASP experiment started. It's a community-wise experiment. It's called Critical Assessment of Structure Prediction. It's a wonderful run. Every 2 years it happens. But what it allowed us, and I'll go a little bit in details of that, what allowed us to, like all the structure modeling community, to really have an honest check how good we are. So that one started in 1994. Okay? And another part, I'll go a little later, which is direct coupling analysis. That's in 2009. So just keep those two in your mind. Okay. So among all the template-free modeling, the molecular dynamics actually is not great at, it's not practical to solve protein structure. It takes a long time. The solvations, the water mod, the solvation is a big part in molecular dynamics. The water models are not exactly the physical water and so on. But in 2010 or something, D. Shaw is a billionaire who decided to come into molecular dynamics world to, and to solve the cancer and so on. He actually designed a dedicated machine, architecture machine called Anton, that is optimized for molecular dynamic simulation in terms of memory, how they communicate with each other. And Anton published a millisecond simulation where they predicted structure of 2 proteins from the scratch. So it is theoretically possible to structure protein structure from AMD. It's just that it's not practical. So the most popular method of template-free is the Rosetta. And it's from David Baker's lab in Washington University. There's a huge community. I think Michael's, your advisor, is from that community too. There is a huge community of Rosetta. They're doing lots of development. The idea behind Rosetta is, again, you fragment your protein between 3 amino acid and 9 amino acid fragments, you collect, you make a fragment library, like if you have these 3 amino acid, what is the structure I find in PDB, and that's your fragment library. And then when you have your query protein, you try to match different fragments by a Monte Carlo simulation. And at this time, you are not adding all the atoms. These are basically, I think, maybe 1 atom per 1 residue or something like that. And then the beauty of David Baker was to come up with the energy function, which is the knowledge base energy function. We'll go in a knowledge base energy function. You just calculate, this is the Bayesian theory. You calculate the probability given a sequence, what is the probability of the structure by calculating from your database, what is the probability of the structure itself, and then given a structure, what is the probability of the sequence and probability of the sequence. So this is like the underlying Bayesian theorem of a lot of the energy function used in this part. Okay, remember if you want to use the molecular mechanics, you have to have all the atoms, and then you represent the atoms as point charge. But here, you do not represent the atoms as point charge. This is coarse grain. Peter will go over a little bit tomorrow, I think, how the coarse grain works. And then once you have the coarse grain model, now you bring the physics terms, and then you get to the final structure. So Rosetta is actually very successful too. And because there have been multiple questions about, especially from Neha, about what is the knowledge-based potential, I wanted to put, so this is like a physics potential. It depends on the distance, depends on the distance of 2 atoms, and so on. A knowledge-based potential is negative log of probability. That's basically a knowledge-based potential, okay? You find a probability, you take the negative log, and that's your knowledge-based potential. And those, how you calculate those probability, that's the tricky part, right? And that's why you have to be creative at how you calculate the probability. So you can see in a knowledge-based potential, you are just calculating, counting, and taking a negative log, versus a physics-based potential, you probably have to worry about charge, distances, and so on. Okay, so as I said, the CASP was a really influential effort in protein structure prediction. Happens every 2 years. The organizers contact other experimentalists and ask them, like, please do not publish your experimental result yet. We can take those experimental results and we can release it, the sequence of the whatever your protein you solved experimentally, to the modeling group. And the sequence is such that you do not find a homology modeling among the current PDB structure. And let's see how well they do. Okay? And it happens every 2 years. Last one is 2020, so this year will be there is another one. So how did we do in terms of protein modeling prediction, right? So on the left-hand side, you have a GDT score. So what does the GDT score do? Let's say you know the correct answer. You know the solved protein structure. Then you have your model. You see, like when you align your model with the protein structure, you calculate how many of the, let's say, C alpha atoms falls within, what fraction of C alpha atoms falls within 1 angstrom or 2 angstrom or 4 angstrom or 8 angstrom. So let's say within 1 angstrom, you have 70% of your C alpha atoms falls when you align with the experimental structure. Within 8 angstrom, let's say that number will be even higher, 90%. So you average over those numbers and you get a total score. So an easy means it's easier to find templates in PDB. Difficult means it's very hard to find templates in PDB. And a rule of thumb is like, if it is above 90, you got everything right. If it is 50, above 50, you kind of got the topology right somewhere. And then if it is 20, it's random, okay? So initially, for a difficult structures, when you said 1994, right? So initially, we are getting structures at random. So we should focus on this part. And you see, as the time goes, we are improving as a community and so on. Until in 2020, there is a huge jump, and that's AlphaFold. Okay. If you take AlphaFold 2 out of 2020 prediction, you get the dotted line. Okay. This is other methods, and when I say other methods, the champions were ITASR and Rosetta. Those are typically the top two. So, and so in a difficult case, you know, the template, if it is for easy, that has been kind of confidently solved pretty long back. The difficult part, you can see like this is around 70. That means like you kind of have the gross topology. You know if it is a beta bundle or if it is alpha helical, you know, but you do not know the details, okay? And then AlphaFold 2 jumped it to almost 90, close to 90, okay? And I'm saying AlphaFold 2, the reason is there was a version of AlphaFold in 2018. That's why we call it AlphaFold 2. However, the DeepMind wants to call it AlphaFold. So those two will be interchangeable. So that was a huge improvement. Right? And that's why we kind of all gravitating towards AlphaFold. Okay. So what happens there? We kind of know the history, we kind of know how much we progressed, and then there's a huge jump. So one of the development that was going at that time was predicting more properties out of MSA. Okay. So this paper came out in 2009, where if we calculate how two residues changes correlatedly, like if one of these mutate, the other one mutates too, then we can infer some ideas between those two residues. And in 2009, there was a paper, and it is very noisy data. There was a paper which came out and cleaned the data. So in that paper, what they were trying to do is like, you calculate MSA of a protein, multiple sequence alignment, and you calculate how one protein, residue correlatedly mutate with another residue. And I'm saying correlation, this is mutual information. You can kind of, if you have a high mutual information between these two, that means you're highly correlated. So you can think like if residue 1 changes, maybe residue 30 changes too, always. So those what you are plotting in this area. The problem with this data is like, just the correlation it can come from a direct interaction or can come from an indirect part. So on this axis, you are plotting calculating what's called direct information. And if you go to a classical correlation definition, this is like what do you call, the next slide has it, will come to my mind. Partial correlation. Okay, so now we'll go through it. So because classical correlation like PCA-based correlation, those relies on linearity assumption. That's why you don't want to do that. You use mutual information or more modern term, which can calculate nonlinear correlation. But just to think, easily, like so on this end, you are calculating correlation between evolution of two residue, and on this axis, you are calculating correlation between direct information between two residues. And in this protein, you can see these are actually two proteins. The direct one, so which will have high direct information here, high correlation here, they are actually at the interface next to each other. And in this part, you have high correlation, but less direct correlation. And you can see they're actually far from each other. So this kind of gives you an idea. If you have an MSA you start getting ideas which residues are close to each other. Okay, so you start getting the idea, oh, from my MSA sequence, I can have a geometric idea. Okay. So again, like, as I said, if you think about classical terms, let's say x1, 2, 3 have a correlation between them of 0.29, 0.62, 0.18. If you want partial correlation, what you do is like, you try to calculate between x1 and x2 correlation, taking the effect of x3 out, and so on. So like correlation between one, partial correlation between 1, 2, when you're taking 3 out, it's their correlation minus that term. The idea behind it is like, you try to see if these two interact directly with each other. And that was the term they're using called direct information. So now I have all the information I need to predict the protein structure, which is I get my MSA. From the MSA, I calculate how different residues are correlatedly evolutionary. And then if I use something like which direct coupling, that gives me a geometric constraints, like these residues should be close to each other, others are probably close to each other. It reminds you of the NMR equation. Remember NMR's experiment. From NMR experiment, you get some distance constraints, and then you do a simulation to try to satisfy the distance constraint. So, like, again, distance constraint, I try to satisfy. From direct coupling predictions, I try to satisfy this geometric constraint. So in theory, I could have, done this, got this result, and remember, this is a kind of like an entropy, like a conservation term. Then I have to transfer it to mutual information, get the distance constraint, and then run this kind of simulation. So in theory, I could have done a structure prediction based from the MSA to distance constraint. The problem is like these are different kind of data, number one, okay? And it's not easy to handle. And also for every protein, you have to do the simulation. So the first person who kind of, I don't know if it's the first person, first paper I saw that who tried say like, you know what, we do not have to do this step individually. We do not have to calculate MSA. We do not have to calculate, we have to calculate MSA, but we do not have to calculate the conservation, like how correlatedly related from the MSA. We do not have to calculate direct coupling analysis and so on. What we should rather focus is on, we feed in the MSA, hopefully our machine learning method learn all these steps and gives us a geometric one. So Mohammad Qureshi published this paper 2019, but I think he had paper before that too, who first said like, we can have an end-to-end differential network where we don't have to go through all these steps explicitly. We can just input the MSA sequences information, and hopefully you'll get a geometric output. And then come the AlphaFold 2. And this is, Daniel will go over a little bit more detail of the infrastructure. The idea is once you have an input sequence, you look for your multiple sequence alignments, okay? And then in multiple sequence alignment from here, you'll get each residue, how coupled are they with other residues. And in this learning structure, infrastructure, which Daniel will explain better, and I do not understand all of it, you end up getting a lot of geometric constraints that you try to satisfy to come up with your final structure. You can use the templates. That means like if your protein has some similar protein, you can take information of that, but it's not necessary. Some of the Google Colab notebook you'll be using, they actually do not use that part. Wherever if you're running AlphaFold on your Exceed, they'll run the full thing. So this is not necessary. You'll still get a good answer just by the MSA sequence and inferring the geometric restraints from that. And then finally, when you have a 3D structure. It may have some steric collision that may not be relaxed. You run a little bit of relaxation for get the final structure. And you'll understand it better when Daniel comes and explain. So one of the reasons that I like AlphaFold is like it has a very decent mechanism of saying like, did I get the structure right or did I not get the structure right, which was mostly absent from previous methods. In the sense like when you get the previous methods, you get a structure, but you don't have an idea like how confident I am on the structure. In AlphaFold, again, I think Dave will explain it a little bit more better. So you have two kinds of confidence. One is called the local confidence, which is like at residue. So level. So what you do is like you take a residue, you calculate, let's say, a C alpha atom. You calculate all the C alpha atom within 15 angstrom of your residue C alpha atom, and then calculate all the distances in your experimental structure. You calculate the same distances in your model structure and see how many of those distances are conserved. That's kind of like the idea of the local distance. It's called IDT score, and the AlphaFold gives a predicted one. And you'll see more, hopefully more, with Dave. Rule of thumb, if it is more than 90, it's highly accurate. If it is less than 50, you probably will get ribbon-like structure and so on. But which is okay. The reason is like just because you got you got something that's not predicted well does not mean you have biological information there. Another part you'll see is called predicted aligned error. That means like in this case, we calculate the error per residue, but you can calculate the error how well one residue is situated with respect to another. And let's see if we can have an example of that. Okay, so to run AlphaFold, again, Dave will go through his Colab Python notebook. AlphaFold 2 has a Colab which is very easy to run. However, the DeepMind group has already solved close to 1 million structure and deposited in their database, okay? So yeah, depending on what protein you're interested in, there's a possibility that structure has been solved and in this database. So look at that first. UniProt database, again, UniProt not only contains structures, it contains the other properties of a protein. They are linked with AlphaFold database so that they, in the UniProt, along with the experimental structure of a protein, you'll get the AlphaFold structure. It's already installed in Exceed, which you have the full version. Again, the Colab does not run the full version. It may not, and then also you cannot tweak things. Exceed, you can tweak things. It was available through Chimera X GUI, which apparently not working since yesterday, at least since yesterday. So that is another option if you are working when hopefully they'll be back again. You can directly predict from Chimera X GUI. So the conclusion is like, if it is a single domain protein, we are highly confident that we'll get the structure. At least we are confident what we are getting right. And that's a very exciting time because now we can go beyond a single structure of protein. We can start addressing the questions at the system level from the structural biology point of view. Okay. So a single domain. Now, when you have multiple domains, and Dave will show you an example of how when you put multiple domains, the relative orientation of the domain may not be correct. And that you get from the PAE score. Okay. So if you predict a multimer with an AlphaFold, there is a possibility that the relative orientation of the domains is not right, and we'll get a hint from the PAE score. And then, we all are excited. We all want to solve everything by AlphaFold. So instead of docking, you can do AlphaFold prediction of two different proteins. But the generalized, ability of AlphaFold to predict a protein-protein interaction is still not well vetted. So it's still, we are not sure yet. Maybe pretty soon it will be. So if you are working with protein-protein complexes, AlphaFold 2 or some of the protein docking might be equivalent at this time. But over the time, it may change. Okay, I think that's all I have. So any questions? If not, I'll pass it to, I can answer questions later too. Yeah, any question? Yes.
Evaluation. So if you get your model through iTester, for example, which is Amnesia, I think, right? And you get a model and you know if it's, you want to know if it's good. So I think there are like several model evaluation tools that you can input your PDB and compare to the structure. Is it worth to also putting like the models from AlphaFold through those evaluation tools to compare what we get to whatever AlphaFold has?
Yeah, so there was a whole field of model evaluation was there when the other template-based modeling was going on, like iTester has a confidence score. None of them are as good as PLDDT. So just trust your PLDDT score. That is the best you have right now. Yes. Yeah.
Is there a maximum size that of like a protein sequence that can be predicted with AlphaFold?
Oh, I'm not aware of any maximum size limit because again, your main driving force is the MSA alignment. As Dave, 600? Okay, so Dave's saying like roughly 600. You're saying 800, okay? Yes. So the question is if we can go around it, one way you can do is like you can break your protein in smaller fraction, then assemble it later. And then also if you have multimers, you can do them individually. Yes.
During one of my modeling project, what I encountered was like whenever the amino acid is like getting longer and longer, the prediction ability gets like really low. So what are your comments about this thing about AlphaFold? Like in iTester, when you go to the longer, when you give the long amino acids protein, generally the means output is not so good. When you are dealing with the 150, 200, it predicts a good structure, and the 30 prediction is very good. What about the AlphaFold? Is it okay like to do with this?
Yeah, so as long as it's a single domain, your amino acid sequence, other than the limit that they said 800 or 600, it should be fine. If it is on multi-domain connected by a flexible linker, then the relative orientation may not be good. The programs like iTest, that is not the case here. So you should be good. Single domain protein, we are very confident. And the other good part is like, when you get your prediction, you know which part you are confident on and you know which part you're not confident on. You might not get all of your protein predicted. You may get certain areas and may not be predicted, but you know that. But I haven't seen any dependence on the length of the sequence. It's more like how much MSA you have available. Yeah.
AlphaFold is basically the AI based. It generates its own parameters to model the protein. Usually, what I use the tool ab initio Rosetta folding protocol, and we have to first, through that, if we do that, we have to first generate the 9-mer and 3-mer fragments by ourselves, which predicts how the 3 residues and 9 residues are going to be in the space, and it generates the fragments. So don't you think that it's much better to just generally means produce those files for specific for your protein rather than this one? Or
I feel your uncomfortableness. We all feel who you come from the physics. We do not know what's going on in there, right? And so that's one part of the AI in the sense like the information that they're basing, we do not have a grasp on it. But having said that, certain fields, and Travis, you can comment, Daniel, you can comment. I have seen certain work where they're trying to, from the AI model, they're trying to go to a lower dimension to see what exactly is going on. But I'm not a specialist. You probably have to talk to them to know about those details. As we grow as a field, we will have a better idea what exactly is being predicted inside the AlphaFold. At this moment, I do not know. Okay, no other questions, and Daniel?